This video is about a light interference experiment. We're going to show you how to do it. This experiment rejects all wave models of light and all wave particle duality models. The idealism of science is that a valid experiment trumps any model. So here we have an experiment which is repeatable. I'm doing this so that an amateur scientist can do this experiment on his own and see for himself the results. Light interference is at the heart of quantum mechanics. If we have a particle model of light that can produce interference, then we question the quantum mechanics. Newton, at around 1700, published his book, Optics, where he proposed that light was corpuscles, that is to say photons, that were being directed by an ether. In the 1800s, 1805, Young published his experiment, a light interference double slit experiment. At the time, the only type of interference that was known was caused by waves, such as water waves and light. So for the last 200 years, light has been considered to be a wave, or in some cases a wave particle. What we see here is going to reject the wave models of light. So this is the experiment. This is just a laser pointer, which is easily available to even amateurs. It's directing its laser beam onto a slit. This is a single slit. It's made out of, here's a business card. We put a hole in the business card and a piece of aluminum foil with a cut in it. The cut is about 1/2 millimeter wide. And you can see the light coming through the slit. Now this produces a diffraction pattern. And there you see the diffraction pattern projected on a white background, which is about 8 meters away. This is the screen image from the light through the first slit onto the screen, which you saw was 8 meters away. This is a normal diffraction pattern. The laser beam is directed onto a second mask. The second mask consists of glass plates. This is just normal window pane glass. And you see here the direct diffraction pattern goes through the glass. Now this part of the experiment is known as the Hodge Experiment, which was explored in an earlier video. This is experiment B, where we put a piece of glass between the first slit and the screen. The glass is transmitting the image fairly well. Now we direct the laser beam and this diffraction pattern through a very narrow slit, about 1/2 millimeter across, between two pieces of glass. You'll see there's the diffraction pattern. This is the third experiment, where we put the slit over the center of the diffraction pattern, and you see what you get here. If you can see these little lines here, those are interference fringes in all the various sections of the diffraction pattern. And here's an expanded view of this area in here. We put a nail in the path of the light, and you can see that the center portion of the light here of the diffraction pattern is totally on the nail. That's to say, the first minima are on each side of the nail. That the light from the center portion, that is to say the light that was going through the slit, is no longer going through the slit, as you can see here. But yet, there's no light going through the slit, but yet the interference pattern remains. And here you see where we put the nail in. The nail is right, this is the shadow of the nail. There's a couple things to notice. One is the diffraction pattern is intact. These are interference fringes, and they are still there when the center of the image is blocked. Another thing I'll note is you see a very faint piece of light right there and right there. And the nail shadow is right in here. So there's no light coming in where the nail is, where the center peak used to be, and we still have interference fringes without light going through the slit. This is the basic Hodge experiment. We had a laser, and we had a single slit screen or mask here, which then let through, and if you remember what this was a regular diffraction pattern that fit the Fraunhofer equation, and then 8 meters away we had the screen. And of course that paper. This comes from that paper. This is a computer toy simulation of the image onto the second mask. That is to say, it's the image from the first mask that's projecting onto the glass plates. This is a regular Fraunhofer type diffraction pattern, which is expected by traditional physics. We put the edge of the glass slit right there and right there, so this part goes through the glass slit. Now, you'll note that that is not uniform distribution across the slit. That's part of the Hodge simulation. The other thing you'll note is some of the light here is impinging still on the glass by the side of the slit. I remarked on that. The blocking nail edges are at the minima of the diffraction image. No light through the slit. Now let's see that. This is the edge of a mask, and here we position the edge right in the middle of the diffraction pattern. The image on the screen of this kind of setup is like this. So here you can see the diffraction pattern on that side, but there's the center of the image. This comes through, but more importantly for this experiment, a lot of light comes through behind the mask. Now, traditional physics explains this. But this is what happens when you put the edge of a blocking mask at the minima of a diffraction pattern. What you see here, and it's kind of hard to follow this down, but still there's a very small amount of light that comes right just inside the mask here, and then the rest of the diffraction pattern follows. The point is that where the center peak used to be, there's no light. This is the simulation of the present experiment, and this then is image C that we saw before. So here you see the peak, here you see the secondary maxima and minima. Now, what we're going to look at next is this part of this image, just to show you these little squiggles, what they are. And this is it. This then is the big peak over here. That's the first minima. And then this is that diffraction pattern. But inside the diffraction pattern, there are these zeros here, which represent interference fringes. So you see the simulation is duplicating the interference fringes and therefore the diffraction pattern. Traditional science requires light to pass through slits in order to form the interference pattern. This experiment places the slits one in front of the other, but we still have a diffraction image, and we still have a second slit that is causing the diffraction pattern to go to an interference pattern. The second introduces the interference friction. This is then a double slit experiment, just not what you usually think of as one. Now, the light from the center of the first slit is blocked. And we saw by putting that edge of the slit at the minima, all the light is blocked. There's no light going through the slit. Therefore, the remainder of the first slit diffraction pattern passes through the glass and is coherent. So you can see this video for a discussion on what coherence is. The resulting interference pattern is not formed by the interference of light through the second mask slit. And of course, the light going through the glass isn't changed either. So therefore, the mere presence of a slit must form the interference pattern. Now, traditional science cannot explain this, and wave models of light don't explain this. The Stowe model suggests the diffraction images, you can see the reference video, and the interference images are formed by reflecting the plenum waves, which direct the photon's path, just like in general relativity. The lack of a reflecting surface in the gap means the remaining part of the mass directs the photons onto the interface pattern on the screen. Light diffraction and interference is at the heart of quantum mechanics. But here we've rejected the wave part of quantum mechanics. But there are three quantum mechanic interpretations that have particle photons. Now, this is not wave packet photons. This is a particle. One is the Bohm interpretation. It suggests that particles, like the Newtonian interpretation, has a position and a momentum at all times. This is a little different than what you hear about when you hear about quantum mechanics. The second quantum mechanic is more of a method of calculating. It's a path integral method. This method takes the Lagrangian, which is to say the action of the plenum wave onto a Hodge, and then does time-space spacings on it. Now, the simulation does the same thing. It takes a look at the action of the waves that are influencing the photon at each for several steps along the way in its path. And okay, the third is a transactional interpretation. Now, the transactional interpretation suggests that a wave that influences a particle's path, one of the waves that influences the particle's path, is coming from the future. That is to say, ahead of where the photon is. Now, in the Stowe model, the waves in the plenum have a speed that's many orders of magnitude faster than the photon, which means the waves from that the photon generates as it travels along, some of the waves go forward, reflect off whatever is in its path, and come back. Okay? So this then is a transactional interpretation where some of the waves that influence the particle's action comes from in front of it. Only in the Stowe case, the waves are not a backward in time thing like the transactional interpretation. They are reflecting from where the photon is going. Wave models of light are rejected by this experiment, including the wave-particle duality kind of models. The Stowe successfully modeled the result of this experiment, as you saw in the simulation patterns. Now, here are the references.